Today, you're going to see non-convex quadratic optimization problems the whole day. There's one component that is just the product of two variables, which we'll look at now in the next half hour. The rest of the day, we'll look at problems where we have multiple product terms, and we are trying to get a tight relaxation for a non-convex problem. From yesterday and from the previous days, you probably realized that the best way to get a decent bound on any optimization problem of the nonlinear form is to take any non-convex set and trying to find the tightest possible relaxation, tightest possible convex relaxation. One classical example, which I think we saw already twice during the course, is one very simple set that is a set in three variables where the third variable is simply equal to the product of the first two. The first two variables have bounds, lower bounds and upper bounds, L1, U1 for x1 and L2, U2 for x2. The convex hull in this case is given by four inequalities of greater or equal type and lesser or equal type. These four inequalities are the most generic, and they obviously hold only when all the bounds are finite. So when their respective bounds are finite, you can write the inequality. And they form a tetrahedron, which is the convex hull of this curve, which represents the product of two variables. So this is x1, x2, and that's x3. So the curve, the colored curve, you saw the same picture yesterday with Sven, has a convex hull that is only formed, even if the curve itself is a set created by a nonlinear function. You only need four inequalities to get the convex hull. There is no other inequality necessary in order to approximate. This is the tightest possible set you can get, tightest possible relaxation you can get. This is old news. It's been discovered in '76, and it was proven to be the convex hull in '83. There are a couple of even more famous cases. So if both x1 and x2 are binary, then you get a product of two binary variables that gives you some form of logic expression. So x1 times x2, where x1 and x2 are binaries, that's simply the logic and between the two variables. And if you just substitute the bounds into the McCormick inequalities, the lower bounds on x1 and x2 are 0, the upper bound are both equal to 1. If you just substitute those, you get those four conditions that were discovered even earlier by Forte for problems with binary variables, which symbolize logical operations. If only one of them is binary, so if only x1 is binary, for instance, and x2 is simply a continuous variable that is switched on or off by x1, then you get something very similar to, well, exactly the big M constraints that are used exactly for doing that, for turning x2 to 0 when x1 is equal to 0, and to leave x2 within its own bounds when x1 is equal to 1. Just by plugging in the bound values into the McCormick constraint. So there's nothing esoteric in here. There is a more general version of this set. It's Mn. It's a multilinear. M stands for multilinear. And it's just a generalization to n greater or equal than 3, where xn is equal to the product of the first n minus 1 variables. And all the first n minus 1 variables have bounds. And clearly, if one of them doesn't have bounds, this set is not going to be bounded. It was proven by Rikun that there is a polyhedral convex hull to this. So it generalized, the tetrahedron that we saw in the previous slide generalizes to obviously a polyhedron with a lot more, actually exponentially many inequalities, but you still need just a polyhedron with finitely many inequalities. The proof of this paper is non-constructive, so actually finding this convex hull is not easy. There is a paper by Meyer and Fludas that find the convex hull for the product of three variables, and it's already a lot more complicated than just four inequalities. But we can take a very easy case and say, what happens in the multilinear case when the lower bound is equal to 0 and the upper bound is equal to 1 for every variable? How would you write the convex hull for this? It doesn't require an exponential number of inequalities. If you think about it, it can be written exactly as you would write the logical constraints. So if you have the logical and between n minus 1 terms, how would you write the linear inequalities describing it? Define it this way. It's the set of x in Rn such that xi is in 0, 1 for every I between 1 and n minus 1, and x of n is the product of them. Product from I from 1 to n of x n minus 1 of x of I. So trivial inequality is that if all the variables are non-negative, obviously the product of them is going to be non-negative, right? If at least one of them is not equal to 1, then obviously xn cannot be equal to 1. So what I'm writing here looks like what the convex hull would be in the case that the variables are all binary and not just between 0 and 1. But that is precisely the case. So let me write this one that's a bit more complicated. I want this x of n to be equal to 1 only when all variables, all n minus 1 variables are equal to 1. How do I write that? If you want a hint, just generalize what we have above. That's pretty much it, just for n greater than 2. So I want to take all the variables, I want to sum them up. So sum for I equal from 1 to n minus 1. And then I want to take x of I. And this sum is going to be between 0 and n minus 1. When it's equal to n minus 1, I know that I want my x of n to be equal to 1. When it's less than that, then I don't want to force xn to anything, so it can be equal to 0. So in fact, I just need to subtract n minus 2 from this summation. You agree with this? This is only one part of it. Now we also need to bound the xn from above. But we can do exactly the same thing that we do there, and we just need to say x of n less or equal than x of I for every I from 1 to n minus 1. The polyhedron described by these n plus 1 inequalities has all binary vertices. So this is also the same polyhedron describing the set where all the x of i's are binary and not just constrained between 0 and 1. So everything is nice when you have as many variables as you want, but there's an important case which we didn't consider yet, and that's when xn itself is bounded. As long as xn is not bounded, the bound on xn are actually given by the bounds on all the other variables. And for example, if all the lower bounds are non-negative, then simply means that the lower bound on xn is the product of all lower bounds. The upper bound on xn is just the product of all upper bounds. In the case when, for example here, when everything is bounded, including x3, things change a lot. We no longer have any polyhedral. So we can have a polyhedral relaxation, but that's not the tightest. So here, for instance, x1 is between 1 and 4, x2 is between 1 and 3. x3 is between 2 and 5, and 2, if you can verify, is greater than the lower bound induced by x1 and x2. And the same holds for the upper bound. 5 is obviously tighter than 4 plus 3, 4 times 3. And Google, say what you wish, is useful for this sort of things. Z equals X times Y. You can plot the function X times Y like this. It's visible enough, right? It's a nice show that it puts on with all the animation. But basically, this is the function. And this function is obviously a saddle. I mean, it's just a product of two variables. But if you put the bound that we just used, I think there were 1 and 4, 1 and 3, and then 2 and 5. What you get, these are, where are the X and Y are red and so this is more or less how the set looks. The red and the green axes are X and Y. If you turn it around, you can see that the function is neither convex nor concave, because if you look it from above, it looks like this, but if you look it from the side, it's not exactly straight. It has a slight bend to it. And the problem with this is the following. If you look from the top, so if you look onto the Cartesian plane X and Y, X1 and X2, what you see is that the contours are curvy. And so, for instance, here you have a convex part of the contour, which means that this is the set. This is just all the set, X1, X2, X3, such that X3 equals X1 times X2, and then these bounds on X1, X2, and X3. So clearly, you cannot no longer have a polyhedral relaxation. You can no longer have a polyhedral convex solidus. What you need in these cases is you will have to approximate at least this curve in such a way that it cuts off some of the non-feasible points, and it will give you a tighter relaxation. Obviously, though, since we have a curve here, what happens is that and we can see it better here, if you add one tangent cut for each such point, you end up with an uncountably many tangent cuts. So one thing you could do is the following, for instance. If you just even if you just consider the two variables x1 and x2, and if you didn't even consider x3, you could look at this set here. So x1 and x2 are between their own bounds, but now there's an extra constraint, which is the product is between L3 and U3. And that means that it's the blue area we're considering. How do you find a valid cut for this set? Well, this part is convex. Actually, you can easily prove that. Actually, I will, it's an exercise in the next slide for you to prove it. This set, if you exclude this other constraint, is convex. And it's okay to prove it. What happens is the following. Take one point on the boundary and and write a tangent cut for it. Tangent cut can be written as another approximation cut. What it will give you, though, and I have to write this on the blackboard because my thick Z skills are not good enough. But if we use x1 here, x2 here, and these are their bounds on x1 and also on x2, what will happen is that this is the curve that represents the fact that x1 times x2 greater or equal than the lower bound on x3. And this is going to be the other curve, which gives you the upper bound on x1 times x2. And this is roughly the blue area that's on the projector. The curve itself, if you consider x3, is going to be something like the one we saw on Google just a few minutes ago. If I can actually plot it. So it's going to be something like this here. and it's going to be something like this here. So if you take the cross section, we do it step by step. If you take the cross section of x1 times x2 at, where is it? This is L3. If you take the cross section of the L3, you're going to end up with this curve. And if you take the cross section instead at U3, this is what you end up at. And it's easy to try and plot it yourself. And the curve is going to look like this, roughly. So this is just the contour of the curve, taking into account the two corners of the feasible area. And the problem with this function is that it's neither convex nor concave. It's a saddle all the way through. And so you can easily just plot it like this, and it's going to have these nice, seemingly convex curves, but only if you evaluate them on a half line. So what happens now? What are we doing here? So let's take into account this two-dimensional drawing and then this very bad three-dimensional drawing. What we just did was take a point x star on the boundary of this set and draw and write an outer approximation cut on it. The outer approximation cut will just give you this lighter blue area, which is obviously a superset of this feasible area, right? In 3D, what does that mean? So if you have an inequality of the form ax1 plus bx2 greater or equal than c, this is clearly going to be in 3 dimensions, simply a hyperplane that looks like this. Sorry, a plane in 3 dimensions that looks like this. You agree it's just tangent at this point on the curve, on the bottom cross section, right? This is already better than we had before, simply because the tetrahedron that we would get without bounds and L3 and U3 would have points outside on the other side of this hyperplane. So we're already cutting some subset of the tetrahedron. But now we want to do something better. What we want to do is the following. This hyperplane here is relatively loose. What we want to do is lift it with x3. And we lift it with x3 simply because now we want to tighten this hyperplane. We want to make it tighter. So we make it tilt by leaning on this curve until it touches this other curve. So it's going to be something, it will rotate like this, I guess, and it will be something like this afterwards. So at that point, it will touch this curve down here and this other curve up here. And it won't cut off any point in the feasible set. This is a graphical explanation. So what is the other approximation cut of the two-dimensional set? The gradient at point x star, so let's suppose we have an x star that's equal to x star 1, x star 2. The gradient of the function f evaluated at x star is a vector that contains the derivative with respect to x1 of a product, x1 times x2. So that means x2 star. And the second component is x1 star. This is the direction that's perpendicular to the plane that you need to write. So the inequality itself is going to be very simple. It's going to be the gradient with respect to the first variable, which is x2 star, multiplied by x1 minus x1 star, plus x1 star multiplied by x2 minus x2 star is greater than or equal to 0. Because this function is equal to 0 at x star, and that means that this tangent, this inequality, gives me the tangent that I was looking for. For now, it's only the vertical one. It's only the one that is not considering x2. But then what do? If I want to lift it, I want to make sure that, is there a question? The function value, the gradient, you mean? We're not taking exactly that. This is, what's the function? Okay, so x3 is equal to x1 times x2. If you take the outer approximation of the function x1 times x2, you're taking a tangent plane to the function itself, which is not going to be an inequality in x1 and x2. We're not using outer approximation the usual way here. We're only using our geometry knowledge to take a tangent line to this curve at this point. You could write another approximation if you took g of x1 equals L3 divided by x1. Because x1 times x2 equals L3, which means x2 is equal to L3 divided by x1. So if you do another approximation of this function, then yes, but you will get something like this. How do we lift it? Lifting this inequality means that now we need to make sure that it both touches the upper curve and the lower curve. In other words, we want it to be like this when x2 times x3 is equal to L3, and we want it to be slightly different when x2 times x3, x1 times x2 is equal to U3. So we want to sum an alpha, which we need to find, multiplied by x3 minus L3. Alpha we don't know, and we can discuss it later. x3 minus L3 is going to be 0 when x3 is equal to L3. So that's fine. If the lifting is actually good, because when x3 is equal to L3, the lifting disappears and we get back our inequality. What is alpha? How do we compute alpha? We need to find the point where the line touches. That's very easy to find for one reason. If this is x star and it touches the curve, then x hat over there is just a multiple of x star. And actually, so if x star, we don't know what x star is, x hat, let's say the contact point on the upper cross section is going to be a beta x star, for reasons that are very easy to prove. So x hat 1 times x hat 2 must be equal to U3, right? X star 1 times x star 2 is equal to L3. This is also equal to beta squared yes, so x hat is equal to U3, but it's also equal to beta squared times x star 1 times x star 2. What does that mean? It's equal to beta squared times L3. So you can figure out what the value of x star is, x hat is from x star. Once you do this, what happens? Well, you simply need to plug in x hat into this inequality, and you will find the value of alpha. So I won't write it because we don't have time. We're actually out of time now. But this, if you plug in x1 star, x1 hat, and x2 hat here, what is x3 hat at that point? At this point, what's the value of x3 hat? It's u3. So if you plug everything here, what you get is a single inequality in alpha only. And it gives you a coefficient for the lifting. This simple trick is, first of all, useful in non-convex mean-law solvers because it serves as a separation method. You want to cut off one point that is arising from solving the linear relaxation, and you also want to make sure that you add a simple linear inequality. However, all of these, well, many of these linear inequalities, and you can add infinitely many of them by just touching a different tangent, a different point on this lower curve. If you put them all together and you lift them all together, I don't advise you to write them all in parametric form, but they will give you a cone. So the set of all the points satisfying all these lifted inequalities is, what did we say yesterday? A cone, because a cone is a very important set. It's a strange cone, though, because it's not exactly a cone with the origin as the vertex. It's a cone with a vertex that is in x hat. Yeah, I used x hat here, but this is another meaning of x hat. This is another point. This other point is, this other value is negative square root of L3 times U3. So what you get is that all of these guys form a cone that has vertex here and has all its, and it's a cone that looks like this. And some of these inequalities are just part of this cone. There's an even nicer result by Anstreicher and others, which says that with this cone you can only include a few of these lifted inequalities. There's another set of inequalities that you can still obtain with the same method, but they are not included in this cone. They're included in other cones. And I didn't say this, but this, apart from the shifting in the origin, is a second order cone.